This is a short overview of the Transactions on Machine Learning Research paper titled Using RKHS Weight Functions in Random Feature Models. The goal of this paper is to analyze the effects of using an RKHS function as the weight function of a random feature model. We call such models RKHS weightings. Our contributions in this paper include algorithms for learning RKHS weightings, theoretical analysis of RKHS weightings leading to several theoretical guarantees, and calculus for several difficult integrals. We run experiments to assess and compare the various methods presented in the paper. Before going any further, let us define the models. A random feature model is an expectation over the sampling of a random feature W of a weight function alpha, evaluated at W, times a Bayes predictor phi parameterized by W. The classic random kitchen sinks assumption on the weight function alpha is that it is bounded. The more general but difficult to use in practice assumption is simply that alpha is square integrable. In this paper, we investigate a third assumption, that the weight function space is an RKHS. So what does an RKHS weighting look like? If K is the kernel of the RKHS, then the weight function alpha is of the form given in equation 2. It will be a weighted sum of partial kernel functions. Inserting this back into the model formulation, we see in equation 3 that an RKHS weighting is a weighted sum of more complex Bayes predictors given by another expectation over the random features. This model can be calculated exactly if the expectation has an analytical form. This is the main advantage of RKHS weightings. In this paper, we present several examples of combinations of feature distribution, kernel, and Bayes predictor that lead to an analytical form for the model. The calculus for these expectations can be found in the paper. These expectations often contain an exponential factor. We show in the paper how to deal with this curse of dimensionality. We provide 3 algorithms for learning RKHS weightings. The first is a stochastic functional gradient descent, which naturally flows from the fact that the RKHS structure of the weight function leads to an easily approximated functional gradient. Our second algorithm is a simple least squares fit. When using the squared loss, an RKHS weighting can be fit very similarly to random kitchen sinks. We can also replace the regularization with an L1 regularization and learn the model with the lasso. This will yield a sparse model. We prove various theoretical guarantees. The first is simply an upper bound on the Rademacher complexity for the predictor class. This bound depends on the RKHS norm of the weight function and a constant that depends on the instantiation being used. Using standard results, we can convert the Rademacher complexity into a probably approximately correct bound. This guarantees that the empirical risk minimizer will be close to the optimal. We also prove that the stochastic functional gradient descent will converge with the rate that we see in equation 4. We have a third, more complex theoretical result, the details of which you can find in the paper. Here is a quick summary of our experiments. The best learning algorithm for RKHS weightings is the least squares fit. It is by far the fastest and results in the best prediction accuracy. The lasso yields good performance, but is the slowest. The stochastic functional gradient descent is faster than the lasso, but has worse performance than both alternatives. Compared to the random kitchen sinks, the performance of RKHS weightings is highly similar, with perhaps only a very small edge. And the performance is similar as well when we consider other classic algorithms, like AdaBoost or SVMs. In conclusion, this paper lays down the foundations for RKHS weightings. They have advantages, like exact model formulations, strong guarantees, and a variety of learning algorithms, each with their pros and cons. RKHS weightings also have drawbacks, such as difficult integrals, the curse of dimensionality, and the choice of instantiation. These are interesting subjects for future research. Thank you for listening. For any question, you can contact me at this address.